Okay, wake up everyone. So if you've been falling asleep for the past 15 minutes, that's okay. Now this is the main talk for today. Okay, I finished my administration duty. Now this is the real scientific science talk. Okay, so are you guys awake now? So please do not fall asleep. No, I don't want to burn my jacket, even though there's no open fire. So how many of you know the title, Charlie and the Chocolate Factory? How many people? Raise your hand if you know this movie. Have you guys watched the movie? Yes. Who was the main character in this movie? Who's the name of the character, not the character, the main actor in that movie? Raise your hand if you know the answer. Johnny Depp. So this is another question, okay? So Johnny Depp is in Los Angeles busy filming another movie. So he's also in Los Angeles at the moment, in Hollywood. That's where I'm from. So because he cannot come here, as much as he would love to come here to give you guys a talk, but he's so busy, you know, filming his next movie. Okay, so he sent me to come here today to give you the chocolate factory version. Okay, so this is more science version than just other cool stuff. Let's get this started, guys. Okay, the Q&A question is ready. I have 10 more strawberry left once again. So those 10 questions will come up really, really quick. So if you know the answer, get it going. Okay, so what we're gonna do today. So basically, I want to first review the 3 state of matters. Okay, that should be easy, and those will be where the question coming from. And hopefully, the talk will be basically teaching you all how to predict physical state and understanding the phase diagram. After that, of course, that will be my favorite, just like everybody's favorite, like a demonstration about chocolate dip strawberry. Okay, let's get it started. Solid, liquid, and gas are the 3 phases of matter, right? Do you guys know that part? Okay, so that means good. So you have been doing a good job. So they still remember the 3 phases of matter. Good. So now you see I have all this little blank right there, right? And I have solid, liquid, and gas in case you forgot what they are. I also give it the Chinese name or an English name and the pictures. Try to remind you what they look like. Now, for the first question, I want to know the order of arrangement among solid, liquid, and gas. And 1 mean the highest, and 3 mean the lowest. And I will need some teacher help to see who is the fastest, okay? Are you ready, teacher? Are you ready? Okay, so who can tell me the answer for number 1? Somewhere over there. You decide. 1, 2, and 3. Is that right? Final? Okay, let's check it out, okay? 1, 2, and 3, so that's correct. Okay, so Sushi got 1. So 9 strawberry left, okay? Watch out, guys. Okay, now this time, density. Once again, I want to find out which one has the highest density among solid, liquid, and gas. Okay? 1, 2, 3. 1, 2, 3. Okay, let's check it out. Yes, that's correct. 1, 2, 3. I have 8 left. Okay. So next question. Ability to compress solid, liquid, gas. Okay. I think you go first. 3 to 1. Okay, say it.
3 to 1.
3 to 1. Is that your final answer? 3 to 1. Okay, that's correct. Okay, ability to compress. 3 to 1. Okay, next question. Interaction with its neighbor. What? Okay. Are you sure? Okay, that's right. Now the next 2 questions is not 1, 2, 3 or 3, 2, 1 or 2, 1, 3 anymore. Okay, the next 2 questions are basically yes or no answer. Okay, fixed volume. Which one has fixed volume? Yes or no? Yes, yes, no? Are you sure? Okay, yes, yes, no? Okay, Okay, I forgot. I forgot. I don't know how many strawberry I have left. Okay, so now, but I think I still have enough at this moment. Last question from this slide. Definite shape. Okay, I think at the back he has been like waiting for a long time. So. Yes, no, no. Let me see. Definite shape. Yes, no, no. Okay, good. So you guys are awesome. Okay, you guys know all the three phases of matter really well right now. Okay, so do not get discouraged. 1, 2, 3, 4, 5, 6, 7, 8. I think I asked about 8 questions, so maybe there should be about 4 left. Okay, so I lost track. So there are 2 ways to change phases. Okay, I think. Okay, I thought my phone was raining, but it wasn't. Normally, you know temperature. Okay, you can change phases. Okay, for example, you have ice. You left it on the table, and it will just melt from solid ice, turn into liquid water, and then eventually, if you decide to pour it, you steam. Just like what I've done earlier, I pour the water, you see steam. So I think this one you're really familiar using heat. I can change from solid to liquid, liquid to gas, and then if I cool it, the steam can condense back into liquid water, and then if I put it in the freezer, it will turn it back into ice again. So this one, I think you guys have no problem understanding that, because you guys put it there all the time. There's another way we can change phases, basically by using the pressure, okay? So if I'm compressing the gas molecule to really confined spaces, I can actually make them turn into a liquid. If I squeeze the liquid water even more, then it will turn into ice, okay? Now, if I reduce the pressure, just let them to run around, just like if we don't give you any chair, just let you guys just randomly sit, you guys are not going to sit like the way you guys are at the moment right now. Okay, so now you guys are like a little solid when I first presenting the admission talk. Now, then the last slide, when I start asking questions and giving away strawberry and chocolate, you guys are like little liquid water. You guys still kind of in the confined spaces, but then you guys have more interaction with me. And then by the time, your teacher says time's up and we have to get going, then you guys left the classroom, you guys will just run like a little gas particle. So just to combine the 2 ideas together, temperature and pressure, we can construct something called the phase diagram. I think this is really important because we don't want to talk about like this particular temperature and pressure, what kind of state would that be? Okay, we try to make everything in terms of graph. A graph is just like a picture. A picture is like 1,000 words. Let's see what we have. We have pressure in here and temperature here. Now, let me go through the term with you really quickly. Anything around this region, to the left of the green lines right here, that's the solid phase. Anything in between the green line and the blue, this is all the liquid region. And anything at the bottom, that's the gas phase, okay? We call them vapor. Most of the substances will look like this green solid line, okay? However, water is slightly different. Water and some other substances, they are slightly different. They have this like a dashed green line. The only difference between these 2 lines, most substances will have a positive slope. And for water, it has a negative slope, okay? That I'll talk about more. Besides that, you have something called the critical point, okay? Oh, actually no, the critical point's right there. We'll talk about the triple point first, sorry. So the triple point meaning that when we're at this particular temperature and pressure, right here, this triple point, all 3 phases can exist at the same time. So, for example, if I talk about water, that means I can have ice, liquid water, and water vapor all existing at the same time at this particular temperature and pressure. It only applies at this specific temperature and pressure. Okay, as soon as I move away from that temperature, it's gone. Only 2 phases, okay? If I'm on any particular spot on this line, that means I only have 2 phases in equilibrium. 2 phases will exist. For example, if I'm on this blue line, that means I can only have liquid water and water vapor. If I'm in here, I can only exist in liquid water form. If I'm in here, that means I'm in steam. So if I'm on the line, that means 2 phases will be in equilibrium. 2 phases will exist. If I'm in here, all 3 phases will exist. Okay, so now if I'm in here, this green line, that means I'm in the solid and liquid 2 phases existing. And I mentioned earlier something called the critical point. Critical point in here means that, once it's beyond this critical temperature and pressure, we enter into this region called the supercritical fluid. What the heck is a supercritical fluid, right? You may wonder. something that looks like water, liquid, but then it's not really a liquid at the same time. You can tell them a gas, but it's not really a gas. Then what is that? Well, I think the best way to do is basically try to show you a video. And I hope the video is working. Okay, yes, it's working. So in here, what you're seeing is that I have some liquid carbon dioxide. I'm heating it up and I hold it in a fixed chamber right here. Basically, as I heat up the liquid CO2, just like liquid water, it starts vaporizing. Okay? Basically, turn into gas phase, just like the CO2 that we breathe out. Now, however, when things start to happen when you're not paying attention, and you just have to stare at it, and then things will start happening. And you can tell me, is that going to be a liquid CO2 or is that a gas CO2? This doesn't look like what we experience in gas, right? Because normally we cannot see gas, correct? And it's not really liquid because it's just kind of filled the whole volume. So once again, we can do this experiment over and over again. As soon as I turn off the temperature, let it condense, cool back, you go back into liquid CO2. Okay, it's a really strange phenomenon. It's between liquid and gas, and this is what we call the supercritical fluid. That's why I decided to show the video, because showing you the video, then you can understand it a lot more. It's hard to comprehend without the pictures. Okay, I think I have shown enough of that one. Okay, so she cannot start. Now, I love CO2. Okay, not only we breathe out CO2, we generate a lot of it. Newspaper talk a lot about it, the greenhouse gas. Now, before we start, let's review what we learned. So, if I have solid to liquid, what kind of transition is that? Solid to liquid. Melting. If I have liquid to solid, freezing. Gas to solid, deposition. Okay, this is something that you don't really experience. Okay, from gas to solid, but maybe you do. We will come back a little bit. From solid to gas is sublimation, liquid to gas vaporization, something that normally you experience. Okay, boiling water, and the reverse process called the condensation. So, what is sublimation? Have you guys experienced sublimation before? What is that? Dry ice, right? So, have you guys played with dry ice before? Yeah, okay, so have you guys used dry ice to mix drinks before? That's what you should do. It's the best thing ever during the Halloween, okay? So let's take a look. In that video, normally when we boil something up, the steam will go up, right? But in that video, it doesn't. Why is that?
CO2.
Raise your hand if you know the answer.
CO2 is heavier than the distance of the air.
Answer than air.
So,
heavier.
So it's same.
So it's same. So that's great. That's correct. Okay, so you get also another strawberry at the end. Now, so if any student interested in like Java, you want to create that special effect, use dry ice with water, it has this really good foggy experience, okay? Or you can, for the next Halloween, you can start making your mixed drink that way, okay? That's really cool, and it's cold. Okay, next question I have, because I'd like to relate everything you learn back into the everyday life. So, how many of you guys have a pressure cooker at home? Or do you guys know what a pressure cooker is? Okay. Pressure cookers are like both. Okay, so now look at the phase diagram that I have in here for the water How does it work? Basically, pressure cookers help you to cook the food faster. Can you try to use the phase diagram to explain this particular phenomenon and how that works? Yes?
Pressure cooker can increase the boiling point of the substance So you can make the thing cook faster and effectively.
So if I increase the boiling point of liquid water by increasing the pressure, how come the food can cook faster?
Because normally for the boiling point of the water is 100 degrees Celsius.
Yes.
And then the food can only like cook under 100 degrees Celsius. Maybe like increase the pressure, the boiling point like is increased by like 120 degrees. So food will be cooked in under 120 degrees Celsius. So it can cook faster as the temperature is higher.
Okay, so that's correct. So that's good. So I mean, at least you remember what happened to the rest of you guys. So by increasing the pressure of the pressure cooker, basically we are effectively increasing the boiling point of liquid water. By burning at a high boiling point, that means we are saving those energy instead of breaking apart those intermolecular force into steam. We keep them into liquid, and all those energy are used to cook the food. That's why we can cook the food longer. Okay, higher boiling point means that all this extra energy are used to boil the food, not wasted and turned into steam. Now this is another video I want to show you. Okay, now this is another interesting property about liquid water. Okay, so let's take a look and see if we can use the phase diagram once again to explain this particular phenomenon. So maybe the speakers up real loud. So basically it has a piece of wire hanging with the weight and put it on top of the ice block. And let's see what happens, okay? So what happened? What did you guys see in the video? What happened to the wire? It cut through the ice, right? It cut through the ice block, but then did the ice block separate into two? It go back into one giant solid ice block, right? So can you use this phase diagram to explain how this happened? Know the answer, don't be shy. I think I could have about maybe 3 strawberries left, maybe 2. Of course I can tell you the answer, but if I tell you the answer, then nobody will get the strawberry. Yes? Okay, so you're saying when the wire press on the ice, it has high pressure, right? And then so what happens if it's high pressure? Okay, you turn the ice into liquid water, okay? So we cut through it, okay? After they cut through, yes? Is it the temperature or what? The pressure will go back, okay? And it turn back to solid, so that's correct, okay? So at the beginning, that's what we have, okay? 0 degrees Celsius, 1 atmospheric pressure, that's where we're living in. By putting weight on that wire, we're increasing the pressure on the ice. So we're actually changing phases from solid to liquid water. And as soon as the water cut through the ice, basically the pressure will be released and it will go back into solid. Okay, so that's why it looks like a little magic. Okay, but actually you can explain this with the whole phase diagram. So I think now from the previous two examples, I think you can understand that the melting temperature and the boiling temperature actually depends on the external pressure, how much pressure we put it on, and that will change. I think this is pretty much what we established from the last two examples. And the temperature at, at 1 atmosphere pressure, that's where we're living at. The water boils at 100 degrees Celsius. Okay. Now let's say we decide, summertime is coming. Maybe we have some time. We can go some hiking at some mountain, right? Let's say we just go climb the Mount Everest, pretty high altitude. So now what will happen? The water will boil at a much lower temperature, that is the opposite at the pressure cooker. And the water actually boils at 70 degrees Celsius, 71 degrees, 70 degrees Celsius. Okay, what does that mean? That means we need to spend more time cooking our food. Okay, bathroom is really difficult to find when you start climbing in the mountain. Okay, so if you don't cook your food long enough, you get a stomach ache. Looking for a bathroom, I think that could be a problem. But again, nobody will be there, so nobody will know what you'll be doing in the mountain. And one last key point I want to talk about, okay, basically is that the temperature remains constant during the phase transition. Okay, so at the beginning, we start from liquid solid, from solid ice at -4 degrees Celsius, we can warm it up back to 0 degrees Celsius. When it hit the 0 degrees Celsius, basically the ice starts melting, the temperature is not changing. All the energy is used to convert back into the liquid water. Once the ice finishes melting, it turns into liquid water. And we can increase the temperature until it hit 100 degrees Celsius, and then water starts boil. After you boil the liquid water, and you turn into steam. So in summary, what you learn from this part, that's not even the demo yet, is that the solid, liquid, and gas are the three phases of matter. Basically, we can use temperature and pressure to change the phase. The melting temperature and boiling temperature depends on how much external pressure we have. And finally, during the phase transition, the temperature remains constant. Now, the second part of the talk is actually more related to chocolate. Okay. Now, we have all these pictures in here. Okay. Chocolate is widely used. We can use it for Valentine's Day, something we just passed, and Easter, which is coming up, Thanksgiving, and the movies, the novels, chocolate. Once again, who is that guy in the picture? No, I'm here. I'm not in the picture. I wish I'm in the picture. So once again, it's Johnny, okay? So somehow, Johnny and I just hook it up pretty often, okay? I saw him walking around in the theater pretty often. So when he come because we have a school, we have a premiere, and Johnny Depp sometimes just walk by and, at the premiere. So I actually saw him a couple times for the movie premiere. So he was a pretty cool guy. He just chill. And of course, we have all this like chocolate and strawberry. So why do I pick this particular talk? Okay, not just to talk about like phase diagram and all that stuff, is that if you actually interested in like cooking and chemistry, I think they're actually quite related, because you want to make really good food, really delicious food, you need to understand how everything works on a really microscopic level, okay, even molecular level. I have taught people how to do ice cream before. I have an ice cream workshop before too, so if you understand how everything works, you can tune the flavor and everything to your like, and people will be more happy. How many of you guys heard about molecular gastronomy before? Molecular gastronomy, 分子料理. Anyone? It's actually pretty cool. It's all about chemistry too. If you understand how chemistry works, you can totally do that at home. Really simple. Okay, you don't have to waste your money to go to some 5-star restaurant. You can do it at home. So chocolate basically have all this different chemical component in here. I don't expect you guys to remember, but just remember a couple of them that's really important. Like caffeine is important because you guys will be spending lots of time studying. So caffeine will basically help you to stay awake as a stimulant. Now dopamine, this is something that, like I said earlier, it feels good. After you eat chocolate, you feel good. Why is that? Because there's a chemical in here called the dopamine, okay? That basically you feel happy and excited. That's why chocolate always have a business there. Now, some interesting things about the chocolate that you may not realize that, okay, in order to grow chocolate, we have to grow the tree, and then basically this is the little fruits inside that. Those are little cacao, the little nuts that we use, okay? This is what we use to make chocolate. To make 1 kilogram of chocolate, basically we need about 300 to 600 of those little beans right there, cacao beans right there. Now the Mayan in the Latin America are the first civilization that used chocolate to make hot chocolate. That's basically what they do. And their hot chocolate basically have a little spiciness in it. They love spicy food. Now, a little bit about the trading part, okay? If you're interested in economics, not only that, sugar and coffee bean they use for trading. Actually, cacao beans are the third largest export in the world at the moment. And even in the old days, we used to use like those shell for currency. And guess what? In Latin America, they use the cacao bean for currency. See, well, let's look at the conversion. If you want 1 turkey, you have to give them about 100 cacao beans. Now, if you want avocados, then you can only give them 3. So for sure, I'm going to save enough 100 cacao beans and get exchange for a turkey, because such a thing is much better deal. Giving them 100 cacao beans, I can get 1 turkey. I can probably live longer. Africa at this moment, basically they produce most of the cacao production at the moment. And every year, we produce about 4.1 million metric tons. 4.1 million metric tons. This is how much cacao bean we're producing back in 2010. And basically, this is my last question to ask you guys. Which country will consume the most chocolate per person? Are you saying I'm fat?
USA.
I'm from the USA. Do I look really fat? Do I look like I eat a lot of chocolate? Not the USA, not Italy, not France, not Brazil, not
Belgium.
not Hong Kong,
Oh, Belgium.
not Belgium,
USA.
Dude, he said no. Canada.
not Africa. They produce a lot. They don't eat a lot. They don't have time to eat a lot. China, they have the most population. That doesn't mean they eat the most chocolate. I'm saying per person, okay?
Australia. Switzerland.
India.
Wait, it's Switzerland.
Switzerland, not India. And guess how much they eat
Guess how
per person?
1 kg.
More than that.
More than that.
Per year. I mean, 1 kg is nothing.
5
Per year.
Or not 1,000 kg. That would be heavier than a building. 100 kg is about 200 some pounds. I mean, I'm about 100 something pounds.
50 kg.
So that means almost twice my size. I mean, that's way too much. How much? Not 50.
25.
I mean, if every person is eating like 50, pounds of 50 kilograms of chocolate, I think they would die.
25.
Less, not that much. About 10. I mean, 10 kilograms is a lot. I mean, per person per year. It's like 10.3. I mean, just because, we Americans look kind of fat, but actually we only about 5.3 kilograms of chocolate. So this fat has to be getting correct, okay? We're fat not because of the chocolate, but for other reasons. Is there a speaker going on? Can I get a speaker? Speaker? Yeah. Or maybe I can put the speaker on. So I'm going to show you the video how chocolate is made for the next couple minutes.
What is it? to water bottle.